So we just looked at polar coordinates, and these are key formulas. This is the formula for position vector, this is the formula for velocity vector, and of course here is the formula for the acceleration vector if you have the position of a point being described by polar coordinates. Okay. Someone asked at the end of last lecture if we need to derive these formulas in the context of an exam, and the answer is no. In the exam, we will not be asking any derivations or expect you to do any derivations of this nature. But primarily, you will have access to these formulas, or you can obviously remember the formulas if you'd like to. But historically, what we've done is provided formula sheets that have these formulas, and you're welcome to use them. And the primary principle is that you know and understand how to use these formulas and what the application of those formulas are. Okay. So one last thing about polar coordinates, the relationship between Cartesian and polar. We already looked at how the unit vectors change from ERE theta to I and J and vice versa. We can also note that if you have theta like so, and this is R, of course, this is Y, this is X, right? So this is X comma Y. So this basically implies, of course, X equals R cosine theta as usual, Y equals R sine theta. And this is if you want to go from R theta to X comma Y, but if you want to go from X comma Y to theta, you can do the following. You can do square root of X squared plus Y squared. So if you do that, of course, that's square root of R squared cosine squared theta plus sine squared theta equals R squared. So R is basically, square root of R squared, which is R. So R is, of course, square root of X squared plus Y squared, which is also just Pythagoras theorem. And you can do tan theta equals Y over X. Okay. So both of those things work for converting from theta to theta to from X comma Y to theta. Now, of course, tan theta, if you do Y over X and tan inverse Y over X, that doesn't tell you which quadrant the theta is. That so you can actually look at sine theta and cosine theta and use the values of sine and cosine to determine whether theta is in the first quadrant, second quadrant, third quadrant, fourth quadrant, right? The first quadrant, both sine and cosine are positive, etc. So recall trigonometry. You can use the sines of sine theta, which is basically X over R, and cosine theta, which is Y over R, to determine the quadrant of theta. Okay. Okay, so that's about polar coordinates. The next topic is tangential normal coordinates. So we'll just do the theory quickly. For polar coordinates, it's pretty straightforward. You just have to remember or use these formulas. It's conceptually pretty straightforward. Tangential normal is a little bit more subtle, I would say, conceptually. It's still straightforward, but a bit more subtle. So let me just write down tangential normal coordinates. Again, it applies to 2D general motion. So it's general motion, but only in 2D. It's not applicable in 3D directly. There's a generalization to 3D, but we will not talk about it. in this course. Okay. Okay, so here's the idea. So let's say you have a particle moving along this path, and at some point here, the tangent vector is, well, tangent to the path, and it's denoted by E sub t, and then the normal to the path is denoted E sub n. And these are both unit vectors, okay? So E sub t is tangential unit vector. E sub n is normal unit vector. Okay. Now, the tangential unit vector is going to be along this way, this way, this way, this way, this way. So it's going to basically be along the tangent to the curve. The normal is interesting. There's a convention here. The normal unit vector is always going to be into the center of the curve. So if the curve is going this way, sort of curving this way, it's going to be pointed toward what is called the instantaneous center of that curve, center of curvature of that curve. So if the curve is going this way, it's going to be pointed this way. If the curve is going this way, the curve is going to be pointed this way. Okay, so I'm going to for here, this is going to be the tangent unit vector, and the normal unit vector is going to be this way. So I intentionally drew this picture like so. Is there a question that sort of arises from this definition? I'll let you guys think about it as I write this down. So always points toward the center of curvature. And perpendicular. So this symbol means perpendicular to E sub t, okay? Okay, so the obvious question is what happens when the curvature changes? So it's curving this way and then curving this way. There's a point in between where it's sort of indeterminate, right? So here it's curving this way, and then here it's curving this way. So the normal vector is this way, this way, this way, this way, this way, until a particular point, kind of an inflection point. And then beyond the inflection point, the normal vector is on the other direction. And at the inflection point where the curvature changes, there is no unique normal vector. You can use either one, I suppose, okay? And that's the convention. You can use either one. Okay, so En is not unique at an inflection point. When curvature changes. Changes sign or direction. And like I said, you can use either one. And then we have another definition. So that's the basic of tangential normal coordinates. This is how the coordinate axes are defined, which is sort of in contrast to polar coordinates. Polar coordinates are defined sort of in absolute terms. Theta is with respect to the x-axis. R, again, is the distance from the origin. And ER and E theta are defined based on, well, the point where you are and then the origin, okay? Here, ET and EN are defined based on, well, the current tangent, the current direction in which you're moving, and also the current curvature, because that determines EN, okay? So let's write that down. Okay, so that's that. And then we have another definition to go. which is called the radius of curvature. Okay, so what's the radius of curvature? So if you have a curve like so, at any point P, there is a local circle that you can fit about that point, and the radius of that circle is rho. Okay, so this is actually, this is the Greek letter okay, it's not a P, it's a Greek letter rho. It's called the radius of curvature. If you want to be a bit more specific, you can call it the instantaneous radius of curvature. Okay, so it's not moving in a circle, but instantaneously it appears to move along a circle of radius rho, and then this rho keeps changing as you move along the curve. Okay, so for instance, if you have a path that is going straight and then starts curving, and then starts curving again, and then starts curving, and then straight, and so on, right? So here, so we can think about when rho is small versus large. This is small rho, right? It's a small radius of curvature, because if you fit a circle here, it's going to be very small. Here, very large rho, sort of intermediate rho. Right, so if you have a straight line, what is rho equal to? And then if you have a point, rho equal to what? Okay. If you have a straight line, rho equals, well, infinity, because you fit a circle and the circle can be bigger and bigger and bigger to essentially make it match the curvature of this curve. So I guess I didn't quite exactly mention how the circle is constructed. I sort of just explained it intuitively, but this circle is technically defined as that circle whose at this point is tangent to the curve, right? But a lot of different circles can be tangent to the curve. This circle is defined as a circle which also matches the curvature. Okay, so if you want to be technical, and think of Taylor series approximations of the curve versus the circle and the curve match sort of your Taylor series approximation up to the second order, basically the quadratic term, they match. Okay, so they match the tangent, which is the slope, but they also match the curvature. But then like third derivative and so on are not necessarily matched. Okay, so that's the definition of this circle. It's sometimes called the osculating circle. And osculating means, I think, kissing, because these curves are kissing in some sense. So it means kissing, I guess. Okay. Anyway, so rho for a straight line, as we said, is infinity. And rho for if it sort of bunches up into a point, it becomes a point of essentially zero radius of curvature. Okay, so that's about radius of curvatures. Okay, let's go back to tangential normal. Now we, just like we have position, velocity, acceleration for polar coordinates, we would like to develop similar formulas for tangential normal coordinates. Now, the tangential normal coordinates doesn't really care about position all that much, because the tangent and the normal are more based on the velocity, so to speak, because there's a direction in which you're moving. So it turns out one doesn't try to represent the position using tangential normal. If you really care about position, perhaps tangential normal is not the coordinate system that you want to use. But the velocity is basically, well, we know that the velocity is going to be along the tangent. So it's going to be velocity v, the vector, is going to be et, right? So this is the direction. And the magnitude, we just use the letter v for that, okay? So this is magnitude. And v is assumed to be greater than 0, okay, by definition, because it's always along et, the velocity, and it's pointed toward et as opposed to et by definition of et. So this magnitude is by definition greater than 0. And then this is the unit vector direction. Okay, so that's the equation for velocity. Again, something you can remember or will be on the formula sheet. And then for acceleration, we just differentiate this expression. It's going to be v dot et. So this is the term that has to do with the rate of change of the speed. So you're going along this path. If your speed changes, namely how fast you're moving changes, that has to do with v dot, and it's changing along et. So this is the term that has to do with speed changes. And then there is v square over rho en. And this is the so-called centripetal term. This is the term that has to do with direction changes. Okay, so term due to speed, and when we say speed, we mean velocity magnitude, speed or magnitude changes. And this is due to direction change. There's a term due to direction change, and it's basically called the centripetal term. Centripetal acceleration. It's always toward the center, right? So En, the normal direction, is defined to be always toward the center of the curve, and that's basically the centripetal term, okay? Let me make this a different color. Okay, sounds good. Maybe I'll do this for this as well. Okay, so this is velocity and acceleration. And again, like I said, you want to remember these formulas. You want to certainly understand these formulas really deeply, but you don't necessarily have to remember them, but remember them helps certainly in your exams. Okay, so it's sometimes helpful to rearrange these equations, so helpful rearrangements. Which is, for instance, if you know v, the velocity vector, and then you can compute the magnitude of the velocity vector, then et is the velocity vector by the velocity magnitude, okay? So for instance, if you knew the velocity in ij sort of directions, then this is going to be the expression for the tangent vector. Another thing that is going to be useful in your problems is the magnitude version of this. So if you knew the magnitude of the acceleration, then that's going to be equal to v dot square plus v square over rho whole square. Okay. Okay, so that is it. These are the main formulas that we will be using. I guess we will end this video for now and then do some example problems.